Welcome to our class. Today we want to discuss Fourier series. If they say that Fourier series, we are familiar with what we call Maclaurin series, Taylor series, and other series like that. But those series are they represent a function in terms of polynomial. For instance, if I take exponential s is 1 plus s squared over 2 factorial plus s cubed over 3 factorial and so on. So this exponential is being represented in terms of polynomial in variable x. But in Fourier, we normally represent a function in terms of sine and cos. That is sine and cosine function. So, or we can say that trigonometry function. So when we express a function in terms of trigonometry function, the type of series is called Fourier series. Now let's take the definition. Fourier series is the representation of general function by sum of simpler trigonometry functions, that is sine and cos. I've just explained that now. When we represent a series in terms of trigonometry function, sine and cos in particular, then that type of series is called Fourier series. So that Fourier series is named after a mathematician. This is the name of the mathematician, Jean-Baptiste Joseph Fourier. So he was the one that established this. Now, before we move on this Fourier, before we give the formal definition of Fourier series, let's first consider a function called periodic function. Periodic function. A periodic function is a function that repeats its value in a regular interval. What that simply means is that function that is repeating its value. For instance, let's assume that the function is moving like this, it's moving like this, it's moving like this. Now, if you look at this, when it gets to this way, they are still on the same level. This one too are still on the same level. They are repeating each other. That is a periodic function. And the great example of that is just sine and cos. They are the ones that are repeating each other like that. Also tan is also a periodic function. So if a function is repeating its value, that is, no matter where it goes to in a regular interval, no matter where it gets to, it will still be the same thing. If you substitute the value, you still get back the same thing. So that type of function is a periodic function. This regular interval here, we call it period. We call it period. It is being represented by t. Now let's give the formal definition of periodic function. We have our formal definition here. A function f of x that has period t is said to be periodic if f of s plus t is equal to f of x. That is, if anywhere we see s, if we turn it to s plus t and it's still giving us back the function, then we say that that function is said to be periodic. That is simply what is here. The definition once again: if a function of s is periodic with period t, then f of s plus t must be equal to f of s. Also, we take note of this: if t is a period, let's say t is a period of any function, then any number multiplied by that t will also be period. 2t, 4t, 5t, and so on. They are also periods. Okay, for instance, if you consider sine s and cos s, they are periodic. So they are all periodic. So their periods are 2, 5. Okay, let me say with period 2 pi. So this is the first period. And from what we have said here now, so the next one will have been 4 pi. The next one will have been 6 pi, that is 2 times t. Since our t is 2 pi, then 2 times 2, 4. 3 times 2, 6, like that. The next one will have been 8 pi. Finally, everything will have been 2n pi. These are the periods of sine and cos. But for tan s is also periodic. Tan s is also periodic with the period of that one is pi, with period pi. Now, how do we even know that these things are periods? Now, let's take note. Let's take sin s as an example. We have said that 2 pi is the period of sin s. The question is that how do we know that sin s is the period? 2 pi, sin s is periodic with period 2 pi. From what we said there, we said that f of s plus t, if it can give you f of s. Now, our f of s is sin s. Now, we consider s plus t. That is, our t, the period there is 2 pi. So we use compound angle to expand this. If you expand this, it will give you sin s cos 2 pi plus cos s sin 2 pi. So when we use compound angle, go and learn that that is sin a plus b. Now, cos 2 pi from your calculator, you take pi to be 180 degrees here. That is cos 3, that is 1. So we have sin s into 1 plus cos s into, this is pi here, cos sin 2 pi, that is sin 360, that will be 0. So what we have left is what? Sin s. As you can see, it gives us back sin s. If it is cos 2, to, let's say that our f of s is cos, to show whether this thing is periodic, we have said that the period is 2 pi as well. We have said period 2 pi, 4 pi, and so on. So to show it, we only need to replace this s. We write that s plus 2 pi, that is f of s plus t. If you expand that one using compound angle, that will be cos s cos 2 pi minus sin s sin 2 pi. So you learn that from compound angle, that is cos a plus b. Now, we have said that the other time that cos 2 pi is simply 1. That is cos 360. Sin 2 pi is simply 0. So what we have left is just cos s. As you can see that cos s plus 2 pi gives me cos s. So any number that behaves so, we say that is a period. So that is that about periodic. Now let's consider a condition that a Fourier series, a function must be satisfied before you can expand it as a Fourier series. The condition is called Dirichlet condition. So the Dirichlet condition is here. The first one is that f of s must be absolutely integrable over a period. So what that simply means is that when we put an absolute value or modulus or magnitude in an integration, this is what it means by it. Let's assume that we have f of x here, ds. So this is what they mean by absolutely integrable. This is absolute value. When we integrate it over a period, it must be integrable. That is, your answer must exist. You must not get infinity. That is the meaning of absolutely integrable. So in any given period, also, f of x must have a finite number of extrema in a given interval. What this means, extrema simply means minimum or maximum. That is the meaning. So it must have finite number of, that simply means that the function must have finite number of maximum or minimum in a given interval. Also, the function must have finite number of discontinuities in any given interval. If they say that discontinuities, for instance, if I say that 2x plus 1 over s minus 1, this function is discontinuous at s is equal to 1. Because if you put s is equal to 1 here, you will have 2 into 1 plus 1 over 1 minus 1. So this is 3 over 0 and it's infinity. So this function is discontinuous here at 1. So we still have three properties of getting continuities, which you must have learned in your elementary calculus. So f of x must have finite number of discontinuities in any given interval, and lastly f of x must be bounded. That is, there must exist an m such that this occurs. So, and what this simply means is that f of x must exist in a certain interval here. So f of x must be bounded, it must be bounded above and bounded below. So if a function satisfies this Dirichlet condition, then we can expand it as a Fourier series. So that will now lead us to the definition of Fourier series. The Fourier series. If a function f of x is periodic, I have explained what periodic function means, and also satisfies the just concluded Dirichlet conditions in this interval minus pi to pi, then its Fourier series representation is defined as this. This is the definition of Fourier series representation. F of x is equal to a naught over 2 plus summation n from 1 to infinity an cos ns plus bn sin ns. You see, this an, a0, a naught, an and bn, they are coefficients of the series. They are the important ones there, which we must discover, we must find. If you have found it, then we can now substitute it. Those are the three things we need only. So the question now is that, what are these three things? A naught, an, bn. These are the three things. A naught is 1 over pi. This is our an, and this is our bn. So this is where the knowledge of integration comes in, which I believe you have learned in your normal integral calculus. However, we can prove this thing easily with this result in this place. So we take note. When we integrate sin s, ns, and cos ns, n is any number, with this boundary, it will be 0, minus pi to pi only. If it is cos m and cos n, cos, or sin, with this boundary, it will either be 0 or pi. It will be 0 if this m and n are not the same thing. But if they are the same thing, then it will be pi. If m is equal to n, it will be pi. Lastly, if you merge sin and cos n together, to be 0. So this one is very obvious. It's a okay. Let us now prove this first one. How do we prove it? The first thing is, let's integrate both sides with this pi to pi, and let's see what we are going to have. You can see it. I have done it here. I have integrated both sides of this thing. I put integration here, integration here, integration here, integration here, with this boundary minus pi to pi. Now, without stressing myself, if I integrate this one, I will have x. So from minus pi to pi. But this one is 0. This one is 0. From what I showed you here, you can see we integrate sin s and cos s from minus pi to pi. Both will be equal to 0. So this is what we have left. If you put s to pi, we have pi. Minus, if you put s to be minus pi, you have minus pi. So that will be plus pi. So this is a naught over 2. Pi plus pi here is 2 pi. This cancels this. So what we are trying to say there is that minus pi to pi, that is this one, what we got is a naught pi. If you make a naught the Fourier formula, you have 1 over pi minus this to this dx. So yeah, as you can see that we have proved the first one of this result. Now it remains this. For this second one, you see that cos n is beside that f, and later they integrated it. So in this case, let us multiply both sides of this by this cos ns, and this will be, I've written it like this. I've multiplied both sides of that function by that. So you can now see that in that place they integrated from minus pi to pi. Let us do the same thing. From minus pi to pi, from minus pi to pi, and lastly from minus pi to pi with respect to x. We don't know what this one will give us. Let's just keep it like that. But we know that this will give me 0 from what I've just shown you. Also, we say that cos ns and cos ns, this cos and cos, we say that if these things are the same, then it will give me pi. Assuming they are not the same thing, this and this, assuming they are not the same thing, it will give me 0. So in this case, it will give me an pi, because the whole of this thing will give me pi. But when you are merging sine and cos together, as you can see, sine and cos, it will always be 0 in this interval. So this one is 0. So what we are, if you now make this an the Fourier formula, you are going to have 1 over pi minus pi to pi f of s cos nx dx. So we have just proved the second result, which is this one. So you can do the third one to yourself. You just multiply this by sin s, just like the way I did for cos. First multiply these two by sin s. At the end of the day, you integrate it from minus pi to pi, and you make use of this. At the end of the day, you need to get sine, and sin, this will give me pi. So it will later lead to what we have here. So in Fourier series, we need to know this 4. 1, 2, 3, 4. This is a Fourier series. But this A naught, A n, B n, they are the ones that have works here, which you must know how to do. If you have known how to find this A naught, A n, and B n, then we don't have problem with Fourier series. So let's take example. Now we have example 1. Find the Fourier series representation of this function. So solution. The first thing we should always take note is our A naught, which is 1 over pi, if you remember, minus pi to pi f of x dx. So this is 1 over pi, but this function is a step function. We have this f of x in two places. So that means this integration will be in 2 places too. Something of this nature. You can see it is from minus pi to pi as well. But the something says that from minus pi to 0. From minus pi to 0, we say that plus 0 to pi. That is the boundary that is given to us. From minus pi to 0 and 0 to pi. Now, what is there is f of x dx. It says that from minus pi to 0, f of x is 0. So this place is 0 dx. It says that from 0 to pi, f of x is 0 to pi, f of x is x. So this place is x. So without much stress, definitely this place will be 0 because of this 0 here. 0 times whatever that is there is 0. What we have left is this 1 over pi. And we can integrate this one. If you integrate this x, you have x squared over 2. 0 to pi. So this is 1 over pi into, if you put, let me bring these 2 out. This is 1 over 2 pi. This will now be pi squared minus, if you put s to be 0, that is 0. So pi cancel pi. What we have there is pi over 2. So we have known our A naught. The next thing we should take note is our A n. We should know. You have to find this. So that one is minus pi to pi f of s cos nx dx. That is our an from the definition of Fourier series that I gave you, as you can see it once again. Now, we are going to have 1 over pi. The function is of two forms, minus pi to 0 and 0 to pi. Let's write them out like this. Minus pi to 0 plus 0 to pi. So the formula says f of s and cos nx. But f of s is 0 there. So this is 0 times cos nx dx. The second one, 0 to pi, says f of s is x. So this is x sine nx dx. So from this place, we have 0 here. Because 0 times whatever will give me 0. So what we are going to have left is 1 over pi. Sorry, this is cos. It's not sine. Cos. From this formula. So we have 0 to pi x cos nx dx. So in this place or in this stage, I don't need to teach you. You need to go through integration by part. Go and learn it. Integration by part. So you solve this thing using integration by part. So when you solve it, what are you going to have? You take this. How do we solve it? We take this. You integrate cos ns. When you integrate cos ns, it will give you sine nx over n. Then you say that minus, you differentiate x. This is 1. You integrate whatever you have here. That is if you integrate sine ns, you have minus cos nx over, there's one n there. As n, another n is coming, we have n squared. So you go and learn how to integrate by part. So this is 1 over this into, if you put s to be pi, we take note of this thing. Sine n pi is 0. But cos n pi, that one is minus 1 raised to power n. So let's take note of these two, and we will be using it in our subsequent solving. If you put s to be pi, we are going to have pi sine n pi. But sine n pi is 0 already. So this will give me 0 over n. It will nullify this one. This one should be plus. There is double minus here. You put cos n pi. Cos n pi is minus 1 raised to power n. Because if you put pi here, it will become cos n pi. That will be that will be minus 1 raised to power n over n squared. In the theory of integration, we normally say that minus the second boundary here. That is when we put s to be 0. In fact, if you put s to be 0, 0 will nullify whatever that is here. 0 times whatever is 0. You know this one is plus already. If you put cos n to be 0, s to be 0, we know that cos 0 from your calculator should give you 1. So this should be 1 over n squared. So that our answer there is 1 over pi. What we have left is minus 1 raised to power n over n squared. Then minus 1 over n squared. So this is the same thing as 1 over pi n squared. N squared at the denominator is common. What we have left is minus 1 raised to power n minus 1. So let's keep this. This is our an. It remains our bn. We remember from the formula that 1 over bn is this. But from the function is in two forms, which I will also write as 1 over pi into integral minus pi to 0 plus 0 to pi. F of s sine s. Our f of x is 0 here. So this will be 0 times sine x dx. The second one is x, the second half, sine nx dx. So which will give me 1 over pi. Everything here is 0 already. 0 will nullify the whole of this side. It is 0 to pi x sine nx dx. This leads to integration by part again. You need to solve this thing using integration by part. So go and learn it. Once again, how do we solve it using integration by part? We take this, we integrate this. If I integrate sine ns, I will have minus cos ns over n. Then I will say that minus, I will differentiate x, that is 1. I will integrate this one. If I integrate this, I will have minus, if I integrate minus cos ns, I will have minus sin nx divided by n. But there's another n here, making n squared. So from minus pi to pi, if we simplify further, so we should have minus x cos nx over n. This will be plus sin nx over n squared minus pi to pi. Now I will substitute the value of pi there. Don't forget that we have said cos n pi is minus 1 raised to power n sin n pi is 0. So let me first put it's no more minus pi to pi, is 0 to pi. It is 0 to pi. That's what we are dealing with. Now let me put s to be pi. So this should be minus pi cos n pi. Cos n pi is minus 1 raised to power n divided by n, plus this one will always give me 0, because if I put pi to be x, sin n pi is 0. So we say that minus when s is 0. When s is 0, the whole of this is 0, because if you put 0 here, it will nullify this. If you put 0 here, it will nullify this. Sin 0 is 0. So we don't need to consider that one. From this place, pi is cancelled. What we have left is minus 1 raised to power n. There's minus here, but since both of them are minus, we can say that minus 1 raised to power n plus 1 over n. So this is our bn. So we have known our an, we have known our bn. Let's write them out. I've written them out here. A naught, we found it to be this. An, we found it to be this. And our bn, we found it to be this. Let us now write out the formula for Fourier series. So we have written them out now. Our A naught, we have known it here. So we only need to substitute these values into this Fourier series, so that our answer is equal to A naught. Our A naught is pi over 2, then divided by 2, plus this. An, we substitute our an there, minus 1 raised to power n minus 1, divided by pi n squared, then cos ns, plus bn. These are bn. Minus 1 raised to power n plus 1 over n, then sin nx. So this is our answer. But you can still simplify this one. This one should give you pi divided by 4. But you can decide to write them out in an expansion form, not in a closed form like this. So that is, if you put n to be 1, minus 1 raised to power this is minus 1. Minus 1 minus 1 is minus 2. So this should give me minus 2 cos x divided by 1 squared. If you put n to be, because n squared is 1, if you put n to be 2, minus 1 squared is 1. 1 minus 1 is 0. So definitely if you put n to be even number, it will always be 0. But if you put n to be odd number, you always get 2 at the top here. So there is 2 here. So this is 2 cos 3s. That is when you put n to be 3. 3 squared minus 2 cos 5x, 5 squared, and so on. it remains these two. When we put n to be 1, so that will be sine x over 1. If you put n to be 2, that is minus sine 2x over 2, like that, plus sine 3x over 3 minus infinity. So which I can finally write out. I've written them together, so they will become this. So this is the Fourier series representation of that given function 0 to x minus pi is less than s is less than pi, and then 0 is less than s is less than pi. So because of the capacity of the video, I'm going to stop here. We'll continue in our next video called Fourier series part 2. We'll continue. We'll have more examples there. Have a good day.